Ever wonder how a packed pallet unfurls into a soft yet supportive mattress? It is an expansive topic you may not want to sleep on. For your own betterment, it may help to learn about a phenomenon known as elastic hysteresis. Hysteresis is the combined effects of latency and path dependence. Hysteresis is the tendency of a system to have more than one stable state over a range of conditions with a response curve that is dependent upon both its current state and past trajectory. Hysteresis occurs when a system is displaced from equilibrium and the system doesn't follow the same path to return to equilibrium. On a coordinate plane, a characteristic lenticular or sigmoidal shape marks a possible elastic hysteresis effect. If an input variable x of t cycles from x sub 0 to x sub 1 and back again, the output y of t may be initially y sub 0, but in a different value y sub 2 upon return. The values of y of t depend upon the path of values that x of t passes through at which it traverses the path. Systems with hysteresis are nonlinear and can be mathematically challenging to model. The Prasich model of hysteresis provides a simplified account of the phenomenon. Under this model, hysteresis is generally described as a relay switch with two thresholds, described by the following argument. If x is less than alpha, the output y is low or off. As we increase x, the output remains low until x reaches beta, at which point the output switches on. Further increasing x has no change. Decreasing x, y does not go low until x reaches alpha again. This system of conditions takes the path of a loop, where the next state depends upon its past state. The elastic deformation of a foam-like material is exemplary of elastic hysteresis. Deformation or strain of a hysteretic material is dependent upon if the applied force is increasing or decreasing over time. As we increase the force or stress on a hysteretic material, the strain remains low until the stress reaches an upper threshold value. Decreasing the stress on the material does not reduce the strain until the stress reaches a second, lower threshold value. In other words, hysteresis describes the activity and time between cause and effect. Memory foam mattresses are made of a class of cellular solids known as viscoelastics, known for their slow response and low resistance to external force. The scaffold-like microstructure of the foam bubbles or cells allow for compression and densification of the material, effectively creating a matrix through which air can move around the cells. This structure decreases the amount of motion that is transferred through the foam by any deformation of the memory material. During the rebound period, energy from the impact is absorbed and dissipated into the cell wall ligaments of the material, while the elastic energy from the foam exerts a force in the opposite direction of the normal force. The resulting time lag literally cushions impact by reducing some of the pressure or impact energy exerted by a body on the material. Mechanical properties of materials are usually modeled by their stress-strain behavior. As a quantity, elastic hysteresis is the difference between the strain energy required to generate a given stress in a material and the elastic energy of that material at that stress. On this stress-strain graph, The upward ramping curve Lm follows a given material's total potential elastic energy, or its response to a load. The downward ramping curve Mn follows the material's elastic energy, or its response to the removal of a load. The area of A between these curves represents the elastic hysteresis of the material. This is the energy that is dissipated as internal friction or heat in a material during one cycle of loading and unloading. The area of B represents the work done by the rebounding foam in the opposite direction of the stressing force. Since materials absorb elastic energy under cyclic stress, the unloading curve is always situated underneath the loading curve. Here is a demonstration of a material exhibiting elastic hysteresis. The foam can support light objects without major deformation to a certain point. If the weight is stacked on top of the foam block, the foam will compress and the volume gets smaller. As more weights are loaded onto it, the foam block will continue to compress because the force exerted by the load on the foam is increasing. Eventually, the foam block will no longer compress and will collapse into a state of equilibrium. Notice that the foam on the left collapses with the addition of a fourth weight. Likewise, our approximate graph predicts the foam does not sharply compress until the load has exceeded a certain threshold. As the weights are taken off, each weight that produced a specific compression displacement as it was placed onto the foam now permits less expansion, resulting in a slightly shorter height. Notice that the foam on the left remains collapsed until the second to last weight is removed. Likewise, our approximate graph predicts the foam does not sharply expand until the load has fallen below a certain threshold. We observe the foam has a lower stress tolerance when it is being reloaded after having exceeded the load capacity of the foam. Contrast this with the higher stress tolerance seen as it was being loaded. The difference between them is equivalent to the strain energy required to generate a given stress in a material minus the material's elastic energy at that stress, which is known as the elastic hysteresis of the material. With proper instrumentation, the hysteresis effect can be measured to better approximate the properties of materials. In this test, a sample of viscoelastic foam is compressed to a fraction of its original height and held for a minute. The compression plate comes back up to little less than its original height of the foam and waits until the foam recovers and makes contact again with the compression plate. Mechanical test data is plotted on a stress-strain curve. A material exhibiting elastic hysteresis will display one path during the loading phase of the test and a different path during the unloading phase. The two paths diverge due to hysteresis loss, or energy loss in the form of heat, with the area between the curves representing the energy dissipated. By analyzing the elastic hysteresis capabilities of different materials, engineers can design a material with properties appropriate for their intended application. A cellular solid like memory foam distributes a load in the intersections and ligaments between the cell nodes. An individual foam cell may configure to one of many microstates or moments. These moments correspond to shifts in the molecular geometry of a complex network of interconnecting cell ligaments. Each discrete cell accumulates and disperses energy in concert with surrounding cells, with maximum deformation near the boundary. The initial moment is characterized by the material at rest or slight reversible bending of the polymer walls. The second moment is that of the compression of cells within the foam from an outside force, where the cells constrict in size and displace the air matrix. The third moment is that of the densification of the polymer walls, where the distance between the cells is constricted in addition to the reduction of the length and dilation of the width of the cell wall ligaments. The particular moment to which a cell could transition is dependent upon what moment it was in before. Here is a simplified explanation of how memory foam exhibits path dependence. A memory foam cell in the first moment cannot immediately transition to the third moment. It must pass through the second moment following the curve to get to the third moment. Likewise, a memory foam cell in the third moment of densification cannot instantly reconfigure into the first moment of rest. It must pass through the second moment as well. In other words, the memory material's future compression or expansion state is dependent upon its prior compressed or expanded state. At rest, foam can only compress. Compressed foam can either expand or densify. Densified foam can only expand. What is possible is structured by the impossible. What is impossible is structured by the possible. Consider the visual pattern of a sequin sheet. Each individual sequin has two stable equilibrium states. Each equilibrium state corresponds to the orientation of a single sequin, determined by which side of the sequin is face up. Each sequin's possible action is structured by its past orientation before a force is applied. If a force is applied with the grain of the sequin remains flat. If a force is applied against the grain of the sequin, it is flipped. Thus, the sequin's orientation is dependent upon the path or direction of a previously applied force. By now, you should have a grip on the concept of elastic hysteresis. While this video focused on materials science, the phenomenon is seen in fields spanning control theory, economics, and electromagnetism. Until next time, rest easy.